Boom. Okay, here are the answers to the trig questions that I gave you. Obviously, there's not enough space here for you to do the problems. So I want you, again, with everything we do, separate lined paper or the blank paper that I have over there by the printer, you can a whole bunch of it, you can put it in your binder. Or if you have your own coil book or your own lined paper or the whiteboards that you're going to use, you can feel free to use all of those things, but do not cram it into the tiny spaces. That said, here are the answers crammed into the tiny spaces. Sometimes. Well, I've given the answers. It's just the answers, not the work. Is there anything there anyone would like me to demonstrate? The first one's 544 meters. Number 2 is 886. Depending on your interpretation for number 3, it's either 0.791 kilometers or 0.807 kilometers, depending on your interpretation of what it means for a target to be 4 kilometers away from the bomber. Is it 4 kilometers diagonally? Is it 4 kilometers horizontally? Because the plane landing on the aircraft, that is the diagonal distance. Because the plane is going down. In the bomber question, the bomb is going down, but the plane is not. And so there's debate as to which one. There's an ambiguity there. We hate ambiguity. On a physics test or quiz, I will not be ambiguous. I will be clear as crystal what I want you to do. But this isn't one of those. So either one of those is totally acceptable. The string on the kite. This is a straight out of my pre-diploma 9. It's identical to, except the name's not Billy. I got it's me actually. 42 degrees is the angle the string makes with the ground. Yes, I made you bomb Rocco's in Mission. Yes. We bombed Rocco's in Mission. Also, the school spirit. I had a question about the school spirit. They made it a literal spirit, like a phantom leaving the school. Oh. And, what was his name? He was only here for grade 9, and then he went to the Fine Arts School. What was his name? I can picture his face. Freckles, big glasses. He was very excitable, had a bowl cut.
It sounds like a fever dream.
No, it was a real dude. It was not a fever dream. Oh, I totally am blanking on the name. I can pull up his yearbook. I'll put his picture in the yearbook. Anyway, totally unrelated. But yeah, we bombed Rocco's because Rocco's suck. Actually, Rocco's is really good. The Rocco's milkshakes are amazing, but if you go and look at the menu, there's a foot-long hot dog and a quarter-pound hot dog, and I asked one night at 1:30 in the morning when I was there with my buddies what the difference is, because a foot-long hot dog could weigh a quarter pound. And the waitress looked at me like I was the stupidest person on the planet. I'm not, and I took offense to this. She said, well, one's a foot long and the other's a quarter pound, and then walked away, and my buddies were doing everything in their power not to completely lose it, because I just got roasted by a waitress at Rocco's at 1:30 in the morning, and I was not pleased. So there's a trig question in my pre-diploma 9 booklet about bombing Rocco's, but the milkshakes are amazing. I will concede this. And I've had students go back and ask about the foot-long and the quarter pound, and they've gotten the same answer. The pendulum question is always a tricky one until you draw it out, and then it becomes a little bit more obvious. The answer is 5.36 centimeters, and the bonus question, which I told you wasn't bonus, I wanted you to do it anyway, is a tricky beast, but the answer is 392 meters. Are there any comments, questions, concerns about any of those? Yes, Seneca. Here it is. In anticipation of you as someone asking the question, I have pre-drawn. Here is the setup. The taller building to the rooftop of the shorter building is 33.1 degrees. The 15th floor, this is not to scale, by the way. The 15th floor to the rooftop of the shorter building has an angle of depression of 21.50 degrees. The distance between the roof and the 15th floor is 101 meters. So this, which means this building is ridiculously tall. Because a floor, like the distance between floors, is between 3 and 4 meters, give or take, depending on the building. So 101 meters means you're looking at like 30 more floors. It's a big building. So this is the setup. You know, you're looking for the horizontal distance between the two buildings, and you've got these two things. We know that this little distance here has to be the same as this little distance here. This is 101, and we don't know the distance between the 15th floor and like the altitude between the 15th floor and this. So I called it x. So what you need to set up are two equations. You're going to have, either way we're looking for this guy, not the diagonal. The diagonal is not going to help us. So we're not using sine or cosine because the diagonal is the hypotenuse. So what you're going to use is tan in both cases. You're going to have the tan of 21.5 degrees is equal to opposite x over adjacent y. So it's going to be x over y. And then the tan of 33.1 degrees is going to equal opposite 101 plus x, because these two have to add together to give you the total vertical distance. 101 plus x over y. Now, I got into an argument with one of my grade 9s yesterday from Mexico. He's like, I have two variables in one equation, and I'm going to solve this thing. I'm like, if you do, you've done it wrong, because it's not possible. If you got two unknowns, you have to have two equations. Here they are. And it's not, I mean, we could isolate for either one of these variables. It doesn't matter. But the easy way to do it is to isolate this thing for y. Sorry, no. Isolate for x and then substitute. So this equation right here is going to become y. I multiply the y up. Y tan of 21.5 equals x. And this one's going to become y tan 33.1 minus, and then brackets on that, minus 101 equals x. And now I have two equations that both equal x. If I have two equations that separately equal the same thing, what must be true of these two equations? They have to equal each other. If this equation equals x and this equation equals x, these two equations must be equal to each other. There's a reason this question is the bonus question. The math skills aren't beyond any of you, but how you use the math skills is certainly challenging. So you're going to have y tan 33.1 minus 101 equals y tan 21.5. And now this is the thing you've got to solve. It's not pretty. It's going to look like this. To make your life a little bit easier, you could punch the tan of 33.1 and the tan of 21.5 into your calculators and get these infinite decimals. But then when you subtract this over, it's a nice subtraction, and we estimate all the time in physics anyway, so let's estimate. The tan of, make sure I'm in degrees, the tan of 33.1 is 0.651891797. So I'm going to cut that off, or I'm going to round it to 4 decimal places. So this is going to become 0.6519y minus 101 equals, the tan of 21.5 is also to 4 decimal places, 0.3939y. I have to get all the y's by themselves. So I'm going to subtract this over, and in the same step, I'm going to add that guy over. So I'm going to get 0.6519 minus 0.3939, and I'm going to get, not as a fraction, 0.258y equals 101. So I'm going to have 101 divided by 0.258, and I really hope that's 392. 391.5. 392. What's 50 centimeters when you're already 391 meters? Y equals 391.5 meters. Again, those math skills are not beyond any of you. By the virtue of sitting here, means you've completed a math in grade 10. Which means all the individual pieces you can do. Just, when you put all those individual pieces together, it gets a little bit more difficult. Seneca, make sense? Happy with that? Again, there's a reason it was a bonus. Nothing I ask you to do this semester will be even close to as bad as this question is. So if you're sitting here already thinking, oh, if this is how it's going to be, I'm going to drop, this is not how it's going to be. If you can do this, you can do anything I'm going to give you and more. Okay. Nope, not that page. That's that's the whole thing. I'm going to give you the filled-in copy. If there are no other questions about trig, find me this page. Here we go. Sig figs. If you've taken Chemistry 11 already, or are in it right now, you've seen this already. If you are IB Math Year 1 with Mr. Keeley, you've seen this last week. I think it was last week. If you have not taken either of those classes, this will likely be brand new to you. Because until you take a physical science, physics or chemistry, the concept of sig figs is not an important one to talk about. We don't talk about it in math. It's a little bit arbitrary until you come to a course like this, or Chemistry 11. Okay, sig figs, short form for what? Sig is short for a few things. I know a guy personally whose name, he goes by Sig, but obviously for a person, Sig stands for... Sorry? No, it doesn't sound for a person, it doesn't sound for significant. For a person, it stands for Sigmund. What? Exactly, that's why he goes by Sig. For numbers, for anything, for any physical object, Sig stands for significant figures. What the heck is a significant figure? I mean, the name kind of gives it away. The English is important here. If something is significant, that means it is meaningful. But when we start talking about the idea of significant figures, as soon as you say, these figures are significant, it implies the existence of values that are not. If I make a big show of declaring that someone is significant, like my wife, for example, should she walk in here, I go on and on and on about how magnificent she is, and then I say nothing else about anything else. The implication is I don't think as highly of you as I do of my wife, which I think is reasonable. So then there must be something that's not significant, and that's what we're going to look at today. What makes a figure significant? What makes a figure insignificant? Before we do that, there are two concepts I want to talk about, and those concepts are accuracy and precision. What is your current understanding of these two concepts? What does it mean to be accurate? In what contexts do we talk about accuracy? You do a game today? What position do you play? Ooh, so it's very important to you that accuracy is a part of what you do. Whose accuracy do you care about as a wide receiver? Being in the right spot. You want to be in the right spot, and the quarterback's got to get the ball to you. Okay? So our concept of accuracy shows up in sport all the time. The issue is being in the right spot. Absolutely. That is the concept of accuracy. Accuracy is how close you are. So in sport am I in the right spot? Will I receive the pass? Will I make the block? Is my throw going to go to the right spot? Did I shoot the bullseye? That's accuracy. A way to talk about that in a slightly more boring scientific way is how close are you to an expected result? So the more accurate you are, the closer you are to where you want to be. On a bullseye like this, typically when we see a bullseye, we're thinking there's three things that we could think of when we talk about bullseyes. All of them involve throwing or shooting. Where do you want to be on the bullseye? Dang it. On the target. The bullseye. whether it's a dartboard or the archery range, or for those of you who might hunt, you want to get it in the middle. So accuracy might look like this. Anywhere around there or right in the middle, one could make the argument that all 5 of those shots are pretty accurate. They're all kind of around the bullseye. Accuracy is how close you are to an expected result. You could just make one shot. Pull the trigger, single shot, boom, there it is on the bullseye. You drop the gun and walk away because you know you're probably never going to do it again. And everyone's like, try again. You're like, no, I peaked. It's done. So if that's accuracy, what's precision? Also sports related. If you are precise, what does that mean in sport? Andre.
I wouldn't say particularly sport-related, but being able to recreate something to an exact detail, pretty much.
You want to be able to recreate to exact detail. Yes. Precision is consistently getting the same result. That's precision. So if you're in sport, it doesn't matter if you can make the throw once. I am not an athlete, but I can stand on the foul line and I can put the ball in the hoop one time. No one's going to pick me for the team because I probably can't do it more than once. Put the ball down, I walk away. You want the guy on the team who can make that shot again and again and again and again and again and again. That's precision. Precision is highly valued. You don't have to be precise to be accurate. I can make the free throw once. I can shoot a 3 one time. Asking me to do it again, probably not going to happen. So these two things don't have to happen together. A way to show precision without accuracy is something that looks like this. Let's say I go to the shooting range or I'm playing out on the dartboard and I get something that looks like that. This is really precise. I put 5 X's there for those of you who can't tell because they're overlapped. This is precision without accuracy. This is accuracy without precision. These shots are not in the same spot. This one's to the left, this one's up, this one's down, this one's right, that one's dead center. There's no precision here. Well, there's less precision here. There's no accuracy here. So this is accurate. This is precise. And the ideal looks like this. Right? That's what everybody wants. You want 5 shots dead center. This is both. But if you can't have one, if you can only be accurate or precise, what do you think, in your heart of hearts, is the better one to be? Why, Saf? You said precision. Why? Would it help if I told you that you're right? Precision is the one that you want. Why? Why did your gut blurt out that answer immediately? This is the better way to be. Why?
Because, like, if you're doing chemistry or something, it's better to be precise about your amounts than it is to be accurate about how much effort you put in it. Like, as in, like, accurate about
Okay, so let's use chemistry as an example. You're doing an experiment. You do the same experiment. You get the same value 3 or 4 times consecutively. Boom, 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 boom. But that answer is wrong every time. What is that going to tell you? You're off by a bit. So what will you then look for? If you're consistently off by the exact same amount, what are you going to look for? A consistent mistake. A mistake. You're somewhere in what you've done, you are making the identical mistake every time, but everything else is perfect. So then all you have to do is figure out what that one issue is, remove it, and now all of those results that you're hitting again and again and again will slide to center. I mean, the same is true in sport. If you are making the exact same, it's a throw. I don't know what it is. Pick a throw. Your quarterback's trying to hit you, Seneca, with a pass, and he's always the same, let's say, behind you. The same throw, he's always, 2 yards back. All the quarterback's got to do is make one tweak. And now all of a sudden, because he's consistently back, if he can figure out that one tweak, now he's going to be consistently on every time. We have in science, we have a language for that. What we call that is systematic error. And of all of the different ways there are to screw up, this is the best way. If you have a systematic error, that means there is a singular flaw that even though you're doing everything else right, is present. And if you can remove it, all of a sudden this will slide to center. If you are precise, it is way better to be precise because you can fix accuracy. But if you are inaccurate, it's a lot harder to teach precision. So if you have to start somewhere, you want to be precise. The example I always use for this is shooting. It's a hobby of mine. Before we had kids, my wife and I were in the process of getting into hunting. We both have our hunting licenses. We both have our gun licenses. And of the two of us, my wife is a scary good shot. First time I took her out shooting, wasn't her gun, it was with my gun. We were still dating at the time. And I gave her my rifle. And I put 3 bullets in it. We went out and we set up some targets out in the bush with some buddies. And she shot the target with my rifle. And there was only one hole with the 3 shots she took. So her, being my wife, not a over... I mean, like everyone struggles with confidence to a degree. She, I missed. Until we went and looked at the target, she did not miss. She hit the exact same hole 3 times with 3 different bullets. Phenomenal. And this is something that she's done again and again and again. My wife is a terrifyingly good shot. Don't want to be on the wrong side of my wife in a rifle. So then we got her hunting rifle and we took her to the range, and the whole process is the gun doesn't come put together properly. You get the gun, you get the scope, you attach the things to each other, and the scopes, for those of you who have never used this, if you've only ever played video games, everything's optimized for you. But in the real world, you have to dial this thing in. If you want to go hunt the deer, the scopes have knobs, you have to fiddle with the knobs to drag in the scope to align it with where the bullet's going to go at the front of the gun. So we took my wife to the range to sight in her firearm. And first time she takes 3 shots, boom, 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 there they were. They're all in the exact same spot. And this is easy to fix. It means we have to drag it. So you tweak the little knobs, and so you need to drag it so the shot goes left and down. We dragged it left and down, and my wife's next 3 shots were right there. Precision is something my wife has been blessed with. She has, again, a phenomenal shot. I am accurate. I am not as precise as she is. This is what my shots will look like. This is how my wife shoots. And so it's better to be precise. Accuracy takes a lot of work to get. Accuracy is easy to get if you're precise. This is luck. This is skill. And you can get both of them by figuring out what that systematic error is. So obviously we're not shooting stuff. I can't take you all to the range because that would be a lot. Also wildly unsafe in the district. Wouldn't be down for that. So let's talk about it in the context of this course. Here's how we're going to talk about this. Instead of shooting things, we're going to do the way more interesting activity of taking some measurement. So here's what I'd like you to do. I'm going to move these. I have a bunch of different tools here. I don't have enough of any single tool for all of you to use the same thing. And this is by design, not by accident. So here they are. I would like you to come grab a tool, and I want you to measure the length and width of your desk. After you have measured, don't Don't talk about your results. Just on your own, with the tool that you grab, decide how you're going to do it and do it. All the desks are identical. That's where it's going to be interesting to see what the results are. Once you've measured the length and the width of your desk, I would like you to come up here. Next to your name, I would like you to put your results. The results are going to look like this. Here's me. I'll put up my results too because I've done this a bunch of times. I want all the lengths to go first. By length by width is how I want you to write this down. So on your marker set, go get a measuring device and measure the length and width of your desk. Once you've made the measurement, put it up on the board. Always metric. We're in physics. It's a science. SI units. You're measuring it in centimeters. Inches are dumb. Inches are dumb.
We use them in the shop all the time, though.
Yeah, you have to use them in the shop. Oh, Vikram, I didn't see you yesterday then. Were you here yesterday? Okay. So no, I'll put it up there. I'll put it up there. I was going with who was here yesterday. I guess I missed you. Vikram. Or Noor is also away. You, that's why you weren't on. You okay? Grab another color if you need. Put your results on the board.
Do it off. That's me.
It was unintentional. You can reach.
Well, the stupidest thing is that sheet metal comes in both metric and material. So you can vary them.
53 by 76, 76 by 53. Oh, you guys are the same.
Yeah.
I want it length by width, so the longer value should always be first.
Yeah, that's what I thought, Violet. Oh, the length.
So Violet was right. So independently, you guys got the exact same results. So Sienna, fix yours.
Thanks for fixing mine.
Well, she made it wrong. She erased your correct answer and then erased it. Don't discuss it with anybody else. Just whatever you measured it to be.
Give me the marker. Okay. I got mine with I was in millimeters. Be mean, but.
And then you can put your tool back on the desk you took it from.
Oh. You also forgot about to go and measure for our schools.
Oh, that's a different class.
Lots of
Math
things.
10.
Ugh.
Math 10, I actually make my students measure the length of the gym using meter sticks. I give some groups, I get 3 different groups. One group has to use meter sticks to measure the length of the gym. One group has to use rulers to measure a single ruler.
Why?
I give them one ruler and they measure the length of the gym. And I give one group this to measure the length of the gym. Yeah, lucky them. And we have a discussion on tools and why we use some of those. Yeah, do what you gotta do. Length and width. Don't share your tools. Everyone needs to use whatever tool that they were given. Why do you have a ruler and a meter stick on your desk? What did you grab first? Okay. Sorry? Next time I will assign measuring devices. That's what I should have.
Yeah, you should.
Wasn't thinking.
Width is left to right.
Width is the shorter distance.
Shorter distance, okay.
Never got it.
What if I got the exact same difference?
So you got a square, your desk is a square. Looking at your desk, you're obviously screwed up.
Well, what if it's just my eyesight?
Then again, systematic error. Something is screwed up. And you need to make an appointment with an eye doctor.
Actually, I have that scheduled for the 16th.
Excellent.
Or no, 18th.
700. What? 56.
Okay.
10 meters long.
We've got some decent alignment here.
709? Yeah.
But we can reasonably go one bit further.
Or we build it small.
You can't reasonably go beyond that.
Okay, so Steven's not here, Zora's not here, and Harpreet's not. No, where's Harpreet? No Harpreet.
That are attendance?
I did attendance already.
You have to measure our desk every time you're.
Okay, so hands up if you got a meter stick. Keep your hand up if you got a tape measure. Like keep your hand. So meter stick hand up. Keep your hands up. Hands up for the tape measure. Okay, maybe I did that the wrong way. Hands down. Hands up if you actually use a ruler. If you use the ruler. So Saf and Gersira use the rulers. Saf and Gersira, where are you? There. Interesting. What is interesting about those two people? Saf and Gersira both use rulers. The rest of you use meter sticks and tapes. What happened? How did those two measurements compare to all the rest of the measurements? All the rest of you didn't have to use a ruler. You have to, yeah.
Yes. A ruler can go across the entire desk, so you have to measure once and then.
It doesn't reach.
Yeah.
So now you have a problem. You have to line up the ruler with where the end was as you move the thing. And so if you look at these results, Saf and Gersira, both close, but if we had to identify, how about Sienna and Violet? What do you guys use? Meter sticks? Okay. On first blush, again, looking at it the second time, there's a few more. But Saf, Gersira, like we can start to identify some that are further away, and that is no fault of yours. You guys were given a crappy end of the stick by getting an inferior measuring device. Some of you guys who used, and I'm noticing there's a lot more decimals amongst those of you who got meter sticks and tape measures. You felt like you wanted to go further, and there was an interesting comment you made, Abdu, as you were walking away from here. You said, this is you said you could reasonably go to 2 decimal places. Why did you feel this way?
Well, the meter stick went up to the first decimal, like the 10th, right? But I felt like I could reasonably assume.
Which meter stick did you get?
For the long ones, the middle ones.
The long metal one. So I wanted you to measure it in centimeters. So the smallest division on one of these things is millimeter, so a 10th of a centimeter. And you said you could reasonably go halfway.
Yes. I don't think you can go beyond that. Or you can't even go like, you can't do anything other than half.
Why? Is that your gut, or did someone tell you that at some point in the past?
No, it didn't seem like it was reasonable to assume.
It doesn't seem like it was reasonable to assume, but you
Yeah.
feel like you could reasonably estimate whether or not you're right on the line or if you're in the middle.
Yes, I couldn't assume the coefficients.
Okay, Andrew.
So for his opinion to be valid, I have to ask you a question.
Yeah.
Are we measuring this from our current standpoint or from the producer, the manufacturer said that this is this long, we measured it this much? From where are we going?
I don't understand the question.
So he's arguing that it's he's going to the decimal point, right? Very, very precise. But are we going that precise, or are we just going to the near centimeter, like a manufacturer would say?
All I asked you to do is measure the desk that you have in front of you with the tool that I provided you to the best of your ability. And so some of you, Abdu was the only one who said, the best of my ability, this is what I can do. And he went to 2 decimal places. He made the assumption that 2 decimal places was reasonable. And he said, well, I'm not directly on 0.6, but I'm not quite at 0.7. I'm somewhere in the middle, but I don't know where in the middle. But the only thing I can assume is more or less halfway. Was what, and then that was the task. I said, to the best of your ability, the tool that you choose, measure your desk. I did this as well. Just to give you a value to compare. I'm not going to hold myself up as the bastion of measurement, but the result I got was, and I felt this, 75.8 by 50.4. Now, take it with a grain of salt whether or not that is the answer. But it is an answer. It's my measurement. I mean, your physics teacher, perhaps, I mean, I'm not going to say I put in more care than anyone, but I'm probably going to put more, especially since I know, like this, I built the lesson, I know where I'm going with this. I probably put in more care than most of you. I mean, there might be some of you here who, like Abdu, definitely put more care in than I did. Because he went further. He felt like he go, or maybe if I wanted to go further, I would put a 0 here for both of these. So largely we're close, right? It's the same language that I've been using. So where's the largest value we've got here? What is the largest value? 76.5. Serena's value is the largest one we've got here for the length. What's the smallest value we have here for the length? I see a set Thor with 75. Is that the lowest? And your Sirat also 75. Okay. So with the lengths, as a class, you guys were between 75 and 76.5 centimeters. Pretty good. That means that's a spread of about that much. Pretty good. The widths are similar from what I can tell. The spread on the width, the lowest one, I was a 50.3. There's a Thor got 50. Anything less than Vikram got 50. Nothing less than 50. Okay, so this is going to be between 50 and what's the maximum length? 51, 52. I think that's a 51. Andrew does his 7s like this. And there's one. Is that the one you're looking at? I already had this conversation with Andrew too. That's allegedly a 1. I think the highest is nope, Sienna and Violet's 53s.
At least you have the same answer.
I mean, if you're gonna be wrong, it's better to have a buddy, right? Who wants to be wrong alone? Okay, so so a bit bigger. 3 centimeters. Now we're looking at just over an inch. Said the forbidden words, the inch. But again, not bad. See, so I have results from last year. Last year's result, the reason I even made the meter 6 available was because my plastic rulers, all the measurements are starting to wash off. And so it's been a lot harder in the past for students to figure this one out. Last year, the spread was this. For the length, the low value was 68.2, and the high value was actually 83. For the width, the low value was 45, and the width was 55. So you guys this year had the benefit of meter sticks and tape measures. I did not give those last semester. Last semester, everyone was using the rulers. I didn't have enough rulers to give all of you rulers. So you guys, given better tools, were able to dial this in a lot further. You're a lot more accurate than my class was last week. Substantially more accurate than my class was last year because you had the benefit of better tools. You can all agree they're all pretty close. What I'd like you to do now is I'd like you to calculate, make sure you have your measurements written down on your page. Because I'm about to erase what's on the board. What I'd like you to do now is using your measurements, your length and your width, I want you to calculate the area of the tabletop. I'll give you a couple more seconds. I'm going to erase what's on the board. Make sure you've written down your measurements. In 5, 4, 3, 2,
2.5.
2.5, 1, 0. Okay. Calculate your area, and I want you to come put that on the board instead. Come give me the area of your desk. Okay.
Square. Yeah, it's a good idea. It's not length. Yeah, big square. Wait, what did you get? Wait, I got 3,800. What were your numbers?
Hold on, I'm not gonna put my number yet.
Minus
Calculate your area, throw it up on the board.
My stomach's really. Yes, ma'am, I'm doing practice. I'm talking to her all. And she went down before I tackled her, and I landed on her knee.
Well, so you didn't get kicked in the knee, you hit someone else with your stomach.
Yes.
That is a fundamentally different description. One implies someone else screwed up, the other implies that you
No,
screwed
because
up.
she fell before I touched her. So I was trying to tackle her, and she fell over. But I was already at that point where my momentum was
You
carrying
committed.
me, and then I fell on her knee.
You fell on her knee, okay. Fundamentally
Hurts.
different than being kicked in the
And then
knee.
whenever I
Or
would
kicked
look
in the
at
stomach.
like a bright light, my stomach would churn.
Oh, that's not good.
So, and then nobody swapped me off for the game because we had 3 swaps, but nobody swapped me, so I was on for like the
So you suffered.
entire 20 minutes.
Game's 20 minutes?
No, it was
Or the
like
half.
practice.
Oh, okay. Scrum.
Just-
No,
just
scrum is
practice.
something else in rugby.
No, scrum is a penalty.
Yeah. Scrimmage. Or is that something else in rugby too?
Yeah, but it,
What do you call a small competitive game amongst your own team on a practice?
that's a scrimmage. Yeah, that's a scrimmage.
Yeah, I would call that a scrimmage, but is that also something in game that means something different?
No.
Okay.
Not that.
Not that you know
No,
of.
no, I just got.
There's a line of scrimmage in some
I-
other sport.
It just made sense of something in the sport, so.
Gotcha.
Advantage sucks. It comes with advantage, and if you touch the ball, the other team has it. Goes back to the point where you fumble. And you have to just, I hate it.
I'll take your word for it. Don't totally follow what you just said, but that's okay. Okay, I want your values on the board. Areas, areas, areas.
I love area.
It's not a hard calculation to do.
Yeah, I just forgot how to do it.
You record everything?
You bet. It's recording right now.
Okay. So do you edit any of it out or you
Nope.
just put the entire thing?
The class as it happened. Some classes I'm like, I can't put that on YouTube. So sometimes
So this is recording?
this is recording right now. You can see on my screen. Like there's,
Oh, that's
it's recording here.
So this is gonna be in the
So
video.
this is this. Oh yeah, this whole conversation is going to be in the video.
Oh,
There's Andrew's fingers, yeah, and there's
If I-
me.
wait. If someone says something out of pocket or like something incriminating, would you delete that from the video or?
I don't edit the videos. Sometimes I don't put the videos up. Like there was one class last year, okay, that I taught Math 9, one student crossed the line and I ripped him apart. I'm like, I can't put that video on YouTube.
It'd make me look
But it was
good.
good because I had 2 Math 9s, and so I just used the same video. Like yesterday, Miss Cruson taught my Math 9s, and I remembered to record one lesson, and I forgot to record the other lesson, but they were the same lesson, so I just put the one video up. Or both blocks.
Well, I'm gonna give you a strike. I'm gonna put
No, you need to go back and sit
You
down.
need to get back to
Okay, you bet. Here we go. Let's take a look at your values. You can also go because I can send out too. Saf, you still don't put it up on the board. Come on. Okay, let's look at your results. These ones are a lot more spread out. Okay, and pro tip in the future, cap the pens, please. They start capped. They need to end capped. Don't be lazy. Okay, areas. Where's the high number? I see some 4,000s. 4,028. There's 3 of them. Boom, boom, boom. Is that the big value? Yep. 4,028 square centimeters. And the low value? There's a 38.5. Is there anything lower than 38.5? 38.2. Match. 37. There's a 37.97. Cool. That's it. 3797.65. This is a much larger spread. 3750. 3750. This is a much larger spread. What's the difference here? 250, 278 square centimeters is the difference here. The difference here was 1.5 centimeters. The difference here was 3 centimeters. You took individual measurements, you guys are all pretty close. You used those pretty close measurements to calculate something new, and now what's this? If we use my result, I don't know if my result's the standard, but my result is 3820. Point what? 0.32 square centimeters. Smack in the middle of your guys's. The point of that second part of the exercise is to see, okay, well, like you guys were close. As a class, you did a pretty good job. 3 centimeters, centimeter and a half. But as soon as you start to take those measurements that you've made, even if they're close, and you start to calculate stuff with them, the differences start to compound in really quite large ways. I mean, the difference here, we said, I'll say it again, 278 square centimeters, which sounds like a lot, but you know, people have a tough time picturing what that means. What does 278 square centimeters look like? Yeah, about that big, Andrew. 278 square centimeters is, what's the square root of 278? 278 square rooted. Boom. It's a square about yay big. Where's my eye in a ruler? Square yay big. That's 278 square centimeters. This is a centimeter and a half. That is 3 centimeters. So this was our difference on our length measures. This was the difference on our width measures. And this is the difference you guys got when you calculated areas. All of a sudden, these things start to compound. And so we need to look at, when we take data, when we look at these things, this is something that we all have to take into account and consider. This leads us to the concept of something called error, which is something I wrote on your guys' page. So, your desk, you've got your values for your desk. And we all, I think we kind of all agreed that you were pretty close. Question is, how close is close enough? There is a, without, I'm not going to do it because the math is beyond what I'm going to get you guys to. You need to have at least a little bit of an introductory calculus to really do true calculations of how close is close enough. There is a whole field of mathematics called error propagation. Thank you, Siri, for the heads up. There's a whole field of mathematics called error propagation, where you can calculate, and there's formulas for it, where you can go through and you can calculate. Propagation means how things grow. When you propagate plants, you're breeding plants and having them grow. So what you're looking at when you're talking about error propagation is, how are my errors compounding as I do things with the measurements that I took? And we can see the errors compounded in a pretty substantial way here. Error propagation. Without doing full-on error propagation, there have been decisions made by people more important than me about what is deemed to be acceptable. And without doing the error propagation, how close do you feel percentage-wise would you consider to be close to an acceptable value? Like, how percent do you want to be off by? 5%, 10%, 20%? At what point, within what range are we going to say, yeah, that's close?
3.
Who said 3? Abdu says 3%. He wants 3% error. Okay. Andrew,
Wait, are we talking about the length and width or the area?
any measurement. 1 to 2. You're saying you have to be within 1 to 2, otherwise you're too far off.
I mean, it depends on what, if it's something really wide and 1% can be a lot.
1% could be a lot if it's a really large measurement. Yeah. I'm going to say right now that the world is thankful that Andrea and Abdu are not the bar. Because the bar is, when we say how close is close enough, without doing proper error propagation, the scientific community has actually decided that 10%. If you are within 10% of the accepted value, you're good. If you are within 10% of the accepted value, you're good. And so what that looks like for what we've done is this. Yeah. So if we're going to take mine as the accepted value, 3820.32, 10% of that is 382. What that means is plus or minus 382. That's the spread that science says, okay, we'll take it. Which all of you land. As soon as we talk about a spread that big, we're in. 1% would have been 38. If we're talking about 1% error, how many of you are out? Anything above 38, 58. Gone. Barely. Gone. Definitely gone. Gone. 38, 58. Seneca, you barely made it. Because it's 382.3. Oh, no. Oh, you're 0.05. You're gone. Gone. Seneca was 2/100ths away from staying in what science would have called acceptable. So all of a sudden we can toss to everyone. Well, not everyone. Almost half of you. Oh, now what's on the low end? What's 38 minus 3,820 minus 38? 3792. Is that right? Yeah, 3792. Anyone below 3792? Gone. Barely. Abdu. You just squeaked in. Below 3792. Emmanuel, barely. 3792. Okay, we only lost 1 on the bottom end. Science says without doing proper error propagation, 10%. Yeah.
But if you wouldn't do that, like, the population of the world could be off by 800 million. 10% is massive.
When you're talking about 9 billion people, 800 million?
What?
You did 800 million? That's 10% of the global population?
Thinking of 8 billion, sorry.
8 million.
Is it 9 billion now? Is it? Population?
I think we're almost at 9 billion. Okay, so
I mean, you don't mind 30%, but still be like a few hundred million. It's not. Like it's,
yeah, but in the grand scheme of the difference between those numbers is substantial. Like, as we conceptualize millions and billions, that's
So with proper propagation, what should that be?
substantial. How you do proper error propagation depends on the calculations themselves. The error propagation will change depending on how you calculate what you're calculating. So if it's just a raw count, you haven't done any calculations with a raw count. Like your guys' measurements. We have to figure out, you've done no calculation. How do we do error propagation for a length measurement? Fortunately, science has dealt with that too. Here's proper error propagation for a length measurement. A measuring instrument generally has a precision of what? Well, Abdu, actually the argument that you made, very kind of in front of everyone, no one was hidden from the conversation that you and I had. You're absolutely right. A measuring instrument generally has a precision of plus or minus half the smallest division. So you are limited by the tool that you choose to use. Fortunately, I think all the meter sticks had the same smallest division. The meter sticks go down to a millimeter, which is 0.1 of a centimeter. So half of that division is 0.05. So Abdu, your argument saying I can reasonably be confident that I can get to half a millimeter, that's exactly what the science, you are completely in agreement with what the scientific community has established as what is a reasonable assumption. So on these meter sticks, you're plus or minus half of a millimeter. So that means that you're plus or minus 0.05 centimeters. And so what that means is, technically speaking, based on that, every single one of these measurements should be to 2 decimal places. Because if the tool that you're using allows for the measurement to go to 2 decimal places, the value you quote needs to be to 2 decimal places. And that goes for the length and the width, the measurements you actually took. You didn't measure the area. You calculated the area, and there's a fundamental difference there. We'll talk about here in a second. Additionally, you're also a source of error. I'd like all y'all to get your phones out and open up the stopwatch. All y'all get your phones out and open up your stopwatch. And we're going to do 2 things with the stopwatch. I would like you guys to hit start and stop as fast as you can. There's mine. What do we get? Give me if you got lower than mine, what was your value? Seneca? Oh, hold on. Oh, sorry. I'm going to write these things down. We're doing it again. Seneca, what'd you get? 0.11. Okay, Vikram? So same thing. Vikram, where are you? 0.11. Sienna?
0.11.
Okay. 0.11.
That's not
Points.
0.10.
Whoa! Look at you go, Speedy. Where are you here? In 0.10. Anybody else? Faster. Kohi. 0.11. Where's Kohi? 0.11. Anyone faster than me? 0.13. Okay.
0.06.
What? Seriously? Nice. Oh, where are you? Here we are. 0.07. Wow.
0.06.
Of course, someone had to beat her. Where are you, Thor? Right here. 0.06. Okay. Slower than me. I only want one person to blend. What'd you get?
0.9.
0.19? Okay. 99. Did you make a mistake? Or is that? No, like.
0.09.
Oh, 0.09. So you're faster than me. 0.09. Anyone slower than me? Was I really the slowest one? I should be the slowest one. I'm the oldest one here.
I'm equal to you.
You're equal to me? Okay. You have the reflexes of a 38-year-old. Congratulations. I should be the slowest one here. As you age, the reflexes slow down. I'm also not an athlete. I would expect my fastest ones to be, depending on what it is, like you guys hone your reflexes in different ways. Honestly, I was expecting better results from a few of you. Seneca, you're wearing a football jersey. I was expecting a better result than me that you got.
I got the same result 3 times in a row.
And this 0.11. So you're consistent. That is your reaction time. And some of you guys are going to be better. I don't know if you've seen videos of this, but there are like basketball players have competed with F1 racers, and there's an activity that they do where someone holds the ball and the drivers put their hands on top. You drop the ball and you got to catch the thing. They've done this with basketball players, and the distance that they catch is pretty big. They've done it with F1 drivers who spend their life right around 390 kilometers per hour. Oh, sorry, right around 300 kilometers per hour. And they're way quicker. The reactions into something you can train. Mine should be the slowest here, because I don't train. I'm the oldest one here. So these, though, are built-in errors to you. Seneca allegedly cannot do better than 0.11. And so what that means is, from your perception of an event to the time that you're able to react to that, is this value in seconds. It's pretty good. But what that means is if you're starting to measure things, that happen very quickly, like one of the labs that we do when I was at UFE, we can't do it here. But if you go to UFE, you take physics, this is a lab you will do. They run it every year. You go up to the top of the bell tower and you drop a marble. Goes down to about 3-4 stories. And you got a time when the thing hits the bottom. So the thing's going to hit, when it hits, you're going to hear the impact, but you got to respond then to that impact. And there's a limit to how quickly you can react to whatever it is you're experiencing. For you guys, you are the source of error in this case. It's not the stopwatch, it's your problem, because the information inside the phone's moving at the speed of light. You're not. Very clearly moving at the speed of light. So you yourself are also a source of error. There's a few things here that show up as your source of error. How you choose to measure. You chose the tools off that table. Some of you were forced to take a ruler. Some of you chose the meter stick. Some of you chose the tape measure. If you're working with a partner and you're over here and they're over there and you're timing something that they're watching, you have to make a choice. How am I going to know who's going to hold the stopwatch? How are we going to know when the thing actually is done? Because if Serena and I are measuring something and I start it and she ends it, if she gets the stopwatch, she needs to know when I start the thing. If I'm holding the stopwatch, I need to know when she hears it end. How are we going to communicate that? So the choices that you make are also a source of error. And then there's your biology. Relates to your reaction time. You are limited by what you are physically capable of doing. You are a source of error. And so I started this by saying we're going to talk about data that's values that are meaningful, values that are significant. We've gotten a long way to get to this point, but all recorded data, any measurement that you take to whatever value you take it to, is considered significant. And that is how we start to get to this concept of what values are significant. You can only talk about values being significant if they are actually raw measurements of particular concepts. And then there are rules for what becomes significant as we start to do calculations with those raw measures. All recorded data is considered to be significant. However, the last digit, whatever it happens to be, is deemed to be uncertain. And this is connected to the error in your measurements and the errors in your calculations. So, here's some sig fig rules. If you did not take the measurement, if someone else took the measurement, and don't worry, I'm not going to cram in a lesson and then give you a bunch of homework, but I'm going to keep going a little bit here. Sig fig rules. If you're just handed a number, here are the rules. All non-zero numbers are significant. So, if I gave you the number 321, how many sig figs are there? Non-zero numbers are significant. So 321 has how many significant digits? 3 of them. Zeros that occur in the middle of a number or between significant figures are also significant. So if I gave you 1001, how many significant figures are there?
4.
Thank you. If I just gave you 1000 though, how many digits would be significant? Only one, only the first one. In in non-decimal numbers, zeros at the end are non-significant. So just what we said. If I gave you 5200, that thing only has how many sig figs? 2. In a decimal number, zeros to the left are not significant. So if I had 0.0085, that only has how many sig figs? Based on that rule, it's 2. And in a decimal number, zeros to the right are considered significant. So if I had 0.2500, that is how many sig figs? Zeros to the right has 4. The zeros after the decimal are considered significant. You're like, why does this matter? We will find out on Monday. You've got no homework from me. You can pack up when the bell goes. See you later. Happy Friday. I hope today was enlightening and slightly enjoyable. We will start looking at how we calculate these things on Monday. On Monday, I want you to start bringing laptops if you've got them. We're going to start graphing after this, and you're going to want your computers for some of that. When the bell goes, you may also go have a super duper day.